Lossy predictive coding. It is a lossy image compression technique. It is what is predictive coding. Predictive coding is the image compression technique. It is based on eliminating the redundancy of closely spaced pixels in spatial or temporal or both on spatial and temporal, by extracting and coding only the new information in each pixel. That new information is the difference of actual and predicted value of the pixel, which is also called the prediction error. Type of predictive coding. It is of two types: lossy predictive coding and lossless predictive coding. It is lossy and lossless. The main difference between lossy and lossless predictive coding is that of quantization step. It is quantization step. Here in lossless it is predictive coding. Prediction error is encoded error free, where prediction error is first quantized and then encoded in lossy predictive coding. Lossy predictive coding, it is image compression technique. The lossy compression techniques building blocks includes redundancy reduction, that is we determine the prediction error. It is quantization, where we quantize that error. Entropy encoding, where we do the symbol encoding to reduce the bitrate. Due to quantization error, due to quantization step, error will be introduced, but higher compression ratio is achieved. Here it is lossy predictive coding encoder, where the fn is the input, f cap of n is the predicted value of fn, that predicted pixel value, en is the error, en is given by en is equal to f of n minus f cap of n, and after quantization e cap we get e cap of n, and here is f cap of n is equal to is fed back to the predictor, where we get f dot of n, that is the reconstructed value of fn. We observe that encoder work on the f dot of n reconstructed value instead of using f of n original available value. It is done because we want encoder and decoder to work on same set of data instead of having different values at encoder and decoder side, because at time of decoding original input original fn is not available to the decoder. So to prevent the error error pile up, error drift at the side of decoder, we use f dot of n at the side of encoder to predict the value. So in the here it is the part of decoder, it is same as this part. So here the symbol is here, symbol comes and get decoded, symbol is decoded, we got e dot of n, and here we got predicted value f cap of n, then we got f dot of n, that is the reconstructed value. So here we write e of n is equal to f of n minus f cap of n. It is the error signal, that is f cap of n generated using the is different order of predictors. That is f cap of n. It is 1D predictor, it is 2D predictor, and it is 3D predictor. Here the pixel arrangement are given and the corresponding neighboring pixels are given. F cap of n, f dot of n is equal to e dot of n and f cap of n. This is the reconstructed signal. So if encoder and decoder operates on different data, then we have drift error, so error building at the. So to prevent that, reconstructed signal is used to carry out the prediction instead of available original signal at the side of decoder. So decoder and encoder both operate on the same data. Predictor, it is the most important part of linear, that is the part of lossy predictive coding. That is the problem statement that we got is we have to minimize that expectation, that is expectation of e square, that is second order moment. We have to minimize the squared prediction error, mean square prediction error. So we get f of n, f cap of n whole square, so that f cap of n is equal to, that is the prediction function f and the past values of x. So here we got f dot of n is equal to e dot of n, f cap of n is nearly equal to e of n, and f cap of n is equal to f of n. So we want f of n is equal to f cap of n, that is, so we use a linear m order predictor, and ai is the prediction coefficient. So we need to determine ai, that is alpha I prediction coefficient for mth order prediction filter or linear predictor, that is alpha I. So there is optimization problem, we need to minimize this part, and this coding approach is referred to as DPCM. It is used in DPCM for generation of alpha I prediction coefficient. So we differentiate sigma with respect to that coefficients, prediction coefficient, and then after differentiating we get this part, and going through that minimizing it through we approach to this final expression of I to m ai r I minus k, which is it is the autocorrelation function, and I minus k is the distance or lag, r of k, this is the distance or lag. Then we get the final expression alpha is equal to alpha into r is equal to r, and alpha value can be determined by r inverse of r, where r is m cross m matrix and r is the vector of length m, and alpha is also the vector of length m. Here we get matrix representation. This is autocorrelation matrix of R, and this is R, that it is the m order vector, and alpha is m order vector. The sum of the coefficients should be less than or equal to 1, so that the allowed range of the input to reduce the impact of transmission noise. Symbol encoder. It is symbol encoder. It is used at the output of the encoder, so to reduce the bitrate. The aim of the symbol encoding is to take the source data and to make it smaller. According to Shannon coding theorem, the number of bits required to encode is directly proportional to the entropy of the source. Is directly proportional. If the information entropy is more, then it contains the more information, so we need more bit to encode it. If it vice versa, if it has less information, we need less bit to encode it. This steps reduces the bit rate in representing the symbol of the source. Various encoding techniques, fixed length coding or entropy coding, static encoding coding, that are being used. Quantization is a major step in lossy predictive coding. We have two types of quantizer: uniform quantizer and non-uniform quantizer. So in uniform quantizer, step size remain constant, and step size are also constant, and predicted value are also constant. They are divided into equal intervals. So if you want to divide the given interval x max plus minus x max into m levels, then the quantization step, that is step size, will be is equal to del of 2x max by m. So it will give me 2x max by m. And here we see that all intervals are same size except the possible for the two outer intervals. So all steps here to here, all steps are same except these. Any value greater than this will be considered will be mapped to highest value, and any value lesser than this will be mapped to the higher value, that is smallest least value. Non-uniform quantizer. The non-uniform quantizer are used so because we try to approximate the input better in the region of high probability, so that the error encountered due to quantization is minimum. So when we see this, the probability density of a signal, if we use non-uniform quantizer, then we get a better result of quantization instead of using a uniform quantizer where the each step size remains a constant. So we get higher error for the values, for the probability, for the values whose probability are higher. So when you use non-uniform quantizer, then we choose larger step at near the lower probability region and final step at the higher probability region, which decreases the average distortion or the prediction error. Sorry, not prediction error, the quantization error. Reduces the quantization error. So design problem, here it goes, as we have to choose bj and yj suitably for, so that we can optimization criteria for the given input probability density function f(x) of x. So by solving these optimization criteria, we need to minimize the quantization error square, that is root square mean square. We have to minimize the mean square error, quantization mean square error. Here we, by minimizing that, we get that value y of j is equal to, this is that summation integral bj minus 1 to j x f of x into x of dx. There we get that it is centroid of the probability mass in that interval. It is a centroid of probability mass in that interval p0 to something like b0 to bi, b that bj minus 1 I minus 1 to bi, and second bj is determined based on yj plus it. Now this is the midpoint of reconstruction level, to neighboring reconstruction level. So we go for optimal max-Lord quantizer design, where x is input signal, yj is the quantizer output, and bj addition boundary, m is level quantizer. Minimization problem is goes, we minimize the mean square quantization error. We define mean square quantization error total accumulated quantization error, mean square quantization error, is given by this. And max load quantizer is the probability density optimized quantizer with non-uniform scalar it is a non-uniform scalar quantizer. So minimization problem goes as we differentiate it with respect to yk, that is output level, and with respect to bk, that input level. Input, that is decision boundary, and output levels, decision boundary. Then we call differentiating with respect to bk, that it is input decision, that input decision boundary. Then we already know that summation resolved to bk only, right? Because the function, because the function summation will be removed, because the function we are differentiating with respect to bk, anything out of that bk will be 0. So when we're differentiating, we'll left with this. After doing the minimization, we get to this. After minimization, we get to this. This is the same derivation, same expression that we have got earlier. With differentiating with respect to quantization level, we use the Leibniz formula, because limits are also the function of function of bk, because we are differentiating with respect to bk, and that it is also function of bk. It is function of bk. That is a function of bk. So performing the Leibniz integral rule on this part and this part separately, we get to this. And after here we getting, after getting yk, then we will get, this part will get cancelled, and yk minus yk plus 1, it can't be equal to 0, so this part has to be 0. So we get to the same expression that we discussed earlier. Implementation, we can implement the lossy predictive coding in two manners, using the differential pulse code modulation or using delta modulation. Delta modulation is the simplest way to do the lossy predictive coding, in which you use one linear predictor, and here it is en, that is step size will be fixed to zeta, and the resulting dm code rate is 1 bit per pixel, because 1 bit pixel code is used here. That is the quantizer used in this code is this. If it is greater than 0, then we keep point plus 0.6.5, and if it less than 0, then we point minus 6.5. The main problem with the dm is that it it undergoes through granular noise distortion, because if step size is larger than the variation of the signal, so it is not able to trace that. And in the case of overlap distortion, signal is varying rapidly in with respect in compared to that step size. So we need larger step size for this, and a smaller step size for granular noise to overcome this problem. DM compression with step size of the plus minus 6.5 and linear row wide 1D scanning has been performed. So here we are reading the image, and here up to here we are showing the image. That performing the delta modulation, PET error, that is reconstruction error, that we want to generate a reconstructed image. Here is that we converting the data to double, because we want to perform the quantization. So at initially data is with data is in the form of unsigned date. Here it is PET error. We are assigning the first row of the original data to that PET error, because we want to do row wise scanning. IM error is the part which is the error which contain the error which will be transmitted through the which from the source. Here we start the row wise scanning, for these two for row and these for column, and here that we took that first value from the first row value from PDR, that is the reconstructed value, and then if any we determine the error by subtracting it from the data value, coming data value, and then we perform that. Then we performed delta modulation. If it is greater than 0, we assign 6.5 to error, or it is minus 6.5. And PDER, that is the reconstructed value, we added that to the previous value, that is f of n, and then we stored that error in IMERR, that is image error, that will be transmitted. So after plotting error signal is plotted, that is the EMR predicted error image. So as doing the decoding part, we take that array of size R decoding of, that is R cross C, okay, and that is I, that is we go for row wise scanning, and we take the first row value, and then we perform that, then we start first row value, and then we perform the reconstruction of that image. we take that we take current pixel is equal to previous pixel value plus that error, the error value that we have, quantized error value that we have received, and we have displayed that reconstructed image. So we obtained the original image here, that predicted error image here, reconstructed image here. We slightly see that that picture has got, that cameraman has got slightly moved. This is due to granular noise distortion, and here we see some type of wear out. This is due to slope overload distortion. So overload distortion. Now that is DPCM, differential pulse code modulation. This part we have already seen in that, in previous slides, that DPCM. The DPCM compression using, we perform the DPCM compression using 4-bit uniform quantizer and 1D linear predictor. Here the image is red, and here the specification of the quantizer is given, that is b is equal to bit rate. We want bits to be 4-bit and levels to be 2 to the power 4, that 2 to the power 4 16. And here we generate the linear predictor, that is the linear predictor will generate alpha is the predictor value, that is the predictor coefficient, that is the prediction coefficient, that is called prediction coefficient, and E is the error image, that we get the error image, total error, we get the error image from the predictor, so we can generate the uniform quantizer, or generating the uniform quantizer. So here we perform the linear predictor, we convert the given data into doubles, and then we find the mean, and then we subtracted that value to the mean to, so that we get the result we performed, we get the smaller value. So we are subtracting the mean, so we get a smaller value, so the calculation can be easy, not easy but convenient. R0 minus R0, that is autocorrelation with zero lag. We perform the 0, that autocorrelation 0, and autocorrelation 1, it is autocorrelation 1, then we perform the coefficient, prediction coefficient R1 divided by R0, we get prediction coefficient here. Then we implement the linear predictor. Here we perform the linear predictor, p is the error to store the prediction error, and we pad that prediction error, that is not in, we pad, it is the error to store the prediction error. Here I1 is we use to generate I1. I1 is the signal that we have used to add an element of padding to the beginning of row using a mirror as to prevent initial row value. We want to prevent the initial row value and store, because using that initial row value we want to do prediction. So for predicting the first row, predicting the first row value, first column value using previous of that. So x hat is equal to alpha into I image I1 r comma c minus 1, that previous column values is minus is that value, and we minus the predicted pixel value, and we get the PE r cross c, that is the error image that we will be transferring it, we will be passing to the main calling function. Here we define the uniform quantizer d min and d max. So mean of, we got error image that we got, mean of that, and mean of that minus 5 times of standard deviation of E and plus 5 times standard deviation of E. Q is equal to quantization, that is quantization is equal to 2 into, that is we already seen that 2 into d max divided by L. Here we divided by 2 because we want steps. Here we have added q2 to rk value, because as we already here, from here we add dr, we are already generating the step size, decision intervals, we are designing decision interval. If we add q2 value to decision interval, then we will get that central value, we will get that output value. If we add to central, if we add low q2 value to the, if we add q2 value to the lower limit of dr value, we will get that level value for uniform quantizer. Here we go for DPC implementation, that PE used for differential image storing, A2 is reconstructed image, and PEQ is quantized image. PEQ is for quantized image. So first we will do row wise scanning. We took total number of rows, and we transfer the first pixel value of a1 to a2. Then we take that previous pixel value, and then here we made predicted value from the previous pixel value, and we goes from first, instead of going, we go from second column to last column, and here we generate PE, that is error image, that we generate error PE minus AI, that is the input value, AI minus predicted value, that we got differential pixel. So after using, here we do the quantization. As we already know, for k I is equal to, that is k is equal to 1 to L, we have L level quantizer. If the value lies between two extremes, then we directly assign the k value to them, to that PEQ. Else we will assign, if it is less than the minimum value, then we assign the minimum value to it, and if it is greater than the maximum value, we assign the maximum value to it. Extreme. And here it is, if xi we generate the previously reconstructed pixel, that it is quantized part plus x hat, that is the predicted part, that is it is the differential, what do we say, it is x hat, it is the predicted part, and PEQ, it is a quantized part. A2 we get, A2 is equal to r comma c, then we assign that value to that, we assign the x1 value to that corresponding location. Then we subplot them, then P is the predicted error image, and PEQ is quantized image, and A2 is reconstructed image. So here we see that I comma and whole, that it is square bracket. This means that minimum value of I is mapped to 0 and that pixel, and maximum value of I is mapped to 255. So we get full range mapping from a mapping of I to 0 to 255. Here we get the result. Original image is this, and predicted error image, we get predicted error image, it is a quantized image, and here it is a reconstructed image with 4 bit per pixel. That's all. Thank you.